Hello everyone, my name is Motaz Ayiad. Today I will be presenting the progress on my topic Enhancement to SCADA EMS for hybrid AC/DC networks. Mainly I will be focusing on my recent publication, Communication Requirements for HVDC AC Transmission Networks State Estimation. Let's start by talking about the modern SCADAs and power systems. Modern SCADAs contains four main layers. In the bottom we have the power system layer, which contains the converters, the generators, the transmission links, and the transmission towers. Above that, we have a data acquisition and monitoring layer, which contain devices that are used to measure and monitor the network, such as IEDs, PMUs, or in general, we call them RTUs, remote terminal units. These devices are connected to the command center of the SCADA through a communication network, which is usually a WAN network. In the command center, we have the operator room, which has a human-machine interface, a screen that basically observes the network and allows the operators to control it and monitor it very well. However, modern SCADA faces new challenges due to the integration of low-carbon technologies, mainly due to the HVDC grids. The HVDC grids require fast reaction compared to the traditional AC grids, especially in the protection side. Therefore, in this work, we explored the components and the structure of the SCADA by going through the remote and the master terminal units, the communication infrastructure, and the operator room. Mainly focusing on the communication infrastructure by exploring the different generations, mediums, and protocols, focusing on the IEC 61850 as a protocol that's commonly used in the AC substations. The main assumption in this work is that the SCADA system is a centralized SCADA for HVAC/DC grids, which means that the two grids of the AC side and the DC sides are connected together in one communication network. And the objective is to cooperate them and observe them simultaneously. From this analysis, we were able to define or identify several challenges that are related to the RTUs, to the agreement between the DC and the DC side of data exchange, and to the communication and time requirements. First, we started by checking the RTUs requirements for HVDC AC. We managed to find out the differences between the DC and the AC RTUs in case of characteristics and the collected measurements. As an example, the DC side requires sensors to work on a very high sampling frequency compared to the AC side. For instance, a 100 kHz versus the 8 kHz for the 50 Hz AC system. Furthermore, the communication protocol that defines the data exchange between the AC and the DC grids is still missing. There are a few drafts available online, like the Transpower one from New Zealand, but still not fully standardized. Time requirement is a critical challenge that comes with the HVDC integration. Many publications suggest that we use the IEC 61850 and the IEEE 1646 as standards for the DC side as they are for the AC side. However, many experimental publications suggest otherwise, as we can see in Table 6 in the highlighted part. To validate our analysis, we established a case study that aims to find the total elapsed time for an HVDC AC state estimation cycle. Another meaning, we are trying to find the total time that elapsed from sensors to RTUs, and from RTUs to data concentrators, then from data concentrators to SCADA, and finally state estimation processing time. The C-grade P4 network is used in this case study. 43 virtual RTUs are installed in different locations of the network, as we can see in figure 8b. These RTUs are collecting data from power lines, converters, and generators, and transmit them to 10 data concentrators, as we can see in figure 8c. And finally, the data concentrators are connected to a centralized SCADA, as we can see in figure 8d. The communication medium is assumed to be fiber optic. In the first layer, we aim to estimate the time delay from the sensors to the RTUs. A simulation test case is implemented in OptiSpice. We can see in figure 10, an electrical optical sensor that transmits 32 bits at 100 megabits per second through a 100-meter long fiber optic cable to the receiver side. In figure 11, we can see the results, where in figure A, we see the generated data and the amplified data. And in figure B, we see the two terminals of the fiber optic cable. As a result, we found out that around 818 nanoseconds is required to send data from the transmitter to the receiver. There is an additional constant guard time delay added by the transponders per sensor, which is usually 20 nanoseconds. Therefore, for 4 sensors, The total time delay in the first layer is around 0.9 microseconds. In the second layer, which represents the delay between the RTU and the data concentrators, first we start by estimating the data that has been generated via RTU. We have three different types of RTUs. First type is the transmission line, the second the converter, and the third is generator. After that, we were able to estimate the transmission delays and the propagation delays by simulating the results on OptiSystem software. On the right side, we can see the figure that represents the outcomes of the OptiSystem for transmitting 210 kilobits in a 100 kilometer fiber optic cable at 1 gigabits per second. There is an additional delay comes from the protocol. In our case is the IAC 61850, and it has been estimated at 37.4 microsecond per RTU. By accumulating the previous delays, we can find out that the second layer delays in a peer-to-peer architecture is around 4.86 milliseconds. But if we use the max pondos, which are similar to the multiplexer, the time can be reduced to 2.13 milliseconds. By repeating the previous steps, we can estimate the time delay from the data concentrator to the SCADA. As a result, in a peer-to-peer architecture, the time delay is around 12.83 milliseconds, but by using the max pondos, the time delay is 10.11 milliseconds. Finally, in the fourth layer, we have the state estimation processing time delay. If we have the time delay for the AC side state estimation and another one for the DC side state estimation, then our assumption that in a unified centralized approach, the total time delay will be larger than the maximum of both. We have used different measurement sets. The maximum one is the 140 measurements, and the time delay in that case was 26.32 milliseconds. As outcomes and results, we found out that in a peer-to-peer architecture, the total time delay is around 44.02 milliseconds. But by using the server-based network, the time delay can be reduced to 38.56 milliseconds. A very noticeable outcome that these delays allow the dynamic state estimation to be implemented. For further details, please have a look at our recent publication, Communication Requirements for a Hybrid VSC-based HVDC AC Transmission Networks State Estimation. Now let's talk a little bit about the current work, which is a continuity of the state estimation, but by improving the bad data detection algorithm by using the statistical method called Gaussian mixture model. GMM models the load and generation profiles from historical data. In our case, I'm using the UK National Grid for January 2021. The SCADA AP4 HVDC AC network is used in this study. As a glimpse of the current work, on the right side, we can see the SCADA AP4 network, which has 4 demand buses. These demand buses are bus number 4, 6, 8, and 11. On the left side, we can see the load profile for each bus. Then I started working on the Gaussian mixture model, trying to estimate the probability distribution function of this load profile, and this is the alpha result. That's it from my side. Thank you for listening. I hope you enjoyed the presentation. Please feel free to ask me any questions. Thank you.
Is it done, Yuri?
No, Comrade Premier. It has only begun.